Okay, so good afternoon, everyone, and uh, let's start today's lecture. And just remind you that next week is a Thanksgiving break, so we do not have any lectures, okay, as well as the recitations. So Monday, Wednesday, Friday, no class and recitations next week, and lecture and recitation will be resumed the week after next one, okay, after the Thanksgiving break. And today's lecture we will separate it by two parts. So the first part we will try to finish the this chapter 7. Okay, this flow similarity, flow dimensional analysis and similitude chapter. Okay, and the second part, if I have time, I will quickly go through the solutions for the our second midterm. All right, so let's start in the lecture first. And also that at the end of the today's lecture, we do have a attendance recording. Okay, just a quiz on the blackboard. So do not leave in the middle. And in the last lecture, we mentioned we introducing the dimensional analysis, right, using that Buckingham pi theorem. So basically, if you introducing that, if we apply that Buckingham theorem, right, to a problem, even without knowing any physical laws, okay, just analyzing the fundamental dimensions for all the input parameters and output parameters, so with that we can reduce, okay, the problem to several you know dimensionless parameters. Okay, so um, your dependent parameter will become a dimensionless parameter, and which will be a function of several dimensionless parameters for independent variables. Okay, and so by doing this way, you will know that we can greatly reduce, okay, the number of independent variables for the problem, so which can be very helpful for us to do the experiments. And so we we continue from there. And the first thing we want to do is that I would like to just give you a list uh, of the dimensionless parameter you commonly will see in the fluid mechanics. Okay, you already see some of them, like the Reynolds number, okay, like the Mach number. All right, and so if you study the fluid mechanics more and more, if you go to each individual specific small area for fluid mechanics, like if you go to aerodynamics, you will see that some parameters, dimensionless parameters like the drag coefficient, those lift coefficients, those kind of things, right? And if you go to the thermal, okay, if you do convection, and if you want to involve the heat transfer, so some dimensionless parameter like the Prandtl number, Nussel number, those things will come into your fluid problem. All right. And if you have flow like the two-phase flow, okay, and so some parameter like the coefficient number will also come into, okay, those kind of things. So but overall, okay, all these dimensionless parameter, they are dimensionless simply means that by the definition of each parameter, right, their physical units, all their units will be canceled out. So the only thing you left is just a number, okay. And this is like a give you several examples, right, to showing you that how we usually just doing to define the dimensionless parameter. Usually just like using a dimensional quantity divided by another dimensional quantity, and these two quantity has to have the same unit. Okay, just like the Reynolds number, right? From the definition Reynolds number, actually, if we're using the viscous force, right, divided by the initial force, okay, and this tau A is viscous force, right? Each will usually has this magnitude, okay, and this is the so if you so you just replace the du with the magnitude of velocity, okay, just thinking like what's the magnitude for this term, and dy like the calculate length to replace dy. So you will get the magnitude for this viscous force is like mu times v times l. And for the initial force, you can do similarly. Okay, what's the initial force? The initial force is m times the acceleration, right? Newton's second law. So this rho is the mass, and acceleration is meter square per second square, right? So it's, you can use this one to get that unit. And you're using this viscous force divided by this initial force, you get this value, and this value actually is the one with the Reynolds number, right? Because we define the Reynolds number as a rho VL over mu. Okay, so this is the way we define the dimension parameter. And similarly, okay, you can also like using the pressure force over the initial force. So you can define a new dimensional parameter like this one using the gravitational force over initial force. You can define another dimensional parameter, and surface tension and the compressibility force and so on. Okay, so this E of mu for this compressive, this sigma here is the surface tension. Okay, the definition of surface tension, and this E of mu here is called the elastic modulus of compressibility. Okay, so basically that this E of mu times A will give you the compressibility force. You do not need to remember this. Okay, this is just some concept introduction here. And so with all this in mind, here I just list that what's a commonly dimensional parameter you will see. Okay, and this page is showing you three most important one. Okay, and what's the definition of Reynolds number? You need to know that. Okay, in simply that is on the top is the initial force, on the bottom you see mu, right? When you see mu, you know that is viscous force. So initial force over the so actually you should replace this to go to down, this to go to up. Okay, so there is a table here. Should be the initial force over the viscous force. Okay, and so this is the meaning of the Reynolds number. And what's the usage of the Reynolds number in fluid mechanics? One important usage is that we can use the Reynolds number to determine either the fluid is laminar or viscous. Oh, sorry, laminar or turbulent. Okay, and which I will give you more example in the next one or two classes, and so that when we're talking about the viscous flow, okay, you will see there, okay, because so this one actually can telling us that whether or not the flow is if the flow is viscous, right? So this is not determined by this Reynolds number. If this Reynolds number is small, the flow is usually laminar flow, and if this Reynolds number is large, so when Reynolds number is large, it simply means that your initial force is much larger than the viscous force. And we know that the viscous force is try to organize the fluid more, more, in more organized way. Okay, so that things is like a flow is flowing just by layer. Okay, but if your initial force is much larger than viscous force, okay, even a very small disturbance in the flow field, that disturbance will not be, will not be what I see attenuated due to the viscous force, so that the flow will become very chaotic. All right, so that the flow can be easily, when Reynolds number become large, flow can be easily become turbulent. And another important thing for dimensional parameter we see in the fluid mechanics is the Mach number, which is already given the we already defined this earlier before, is the velocity over the sound speed. Okay, and Mach number is a special one because that they have, they have two different kind of meaning actually, but they are all just using the same parameter. You can using the Mach number to determine that just simply using the Mach number to determine that the flow speed. Okay, if Mach number is smaller than 1, it's subsonic flow, and if Mach number is larger than 1, it's a supersonic flow. Okay, and if Mach number is larger than 5, 10, we even call that hypersonic flow. And not only the speed, okay, there is another important meaning, okay, for the Mach number is that it also characterizes the compressibility of the flow. Okay, and why? Okay, you just simply need to do some further, manipulation for this definition of Mach number. You just change this sound speed with this dp over d rho. So this is the definition of sound speed in the thermodynamics. Okay, and this dp here, this is showing you that the change of the pressure due to the density, right? And it can be rewrite this dp over d rho with this ev over rho. Remember, this ev is the same ev here. showing you the compressibility force, because it's showing that the force will be like due to the change of the density. And so if you do this manipulation, you can rewrite your Mach number in this form, manipulated in this form. And on the top, rho v squared, so this is the initial force. Okay, on the bottom, it's the compressibility force. Okay, so in another word, Mach number is also, showing you that the ratio between the initial force and the compressibility force. And that is why usually, okay, when Mach number is small, when Mach number is small, Mach number is smaller than 0.3 in in engineering, which means that your initial force is much larger than your compressibility force. So we consider the flow is incompressible. Okay, and when Mach number is larger than 0.3, we consider the flow is compressible. So in another word, okay, for the aerodynamics problem, when you have a large Mach number, like those, aeronautical, astronautic problems, okay, usually you have a large Mach number, and usually the flow will be compressible flow. And that is why that you will see those, behavior, like anytime you see that those shock wave, right, Mach disk, those kind of things. And you see the shock wave, Mach disk, those flow structure, you see those is because that they have very sharply change of the density in a small region. That's the reason you see the shock wave. The density, the flow density across the shock wave, they will change greatly, So that's why is that you only see those aerodynamic behavior for the compressible flow, because Mach number is large, flow will become compressible, density will going to be changed. Okay, and so this is the second very important parameter we are going to use for the fluid mechanics, Mach number. And the next one is basically try to estimate. Remember that in this here, if you want to do the gravity force over the initial, you get this G of L over V squared, right? And so this is just the so this basically is just the 1 of FR squared. Okay. So we define this FR, call this float number. So it's showing you the okay. So this is should be convert. It should be going back. So this is switched order. Okay. Is from its definition, right? You see this on the top is the velocity, right? So this is the initial force, and on the bottom you see this gravity here. So this will showing you the gravity force. So this float number is the ratio between the initial force and the gravity force. So when this float number is becoming important, it's in the cases that when you cannot neglect the effect of the gravity. Okay, flow gravity. Like if you do some experiments, right? Like what I see. Like if you study the flow over a horizontal tube, right? Usually this flow number is not that important. But if you study the flow over a vertical tube, then this flow number you have to be included into your consideration in your experiments, because that we know that for the flow in a vertical tube, the gravity definitely will play a role, especially when in the cases this tube diameter is large. And if the tube diameter is small, and because that surface tension effect, so maybe the gravity is not that important. Okay, maybe in that case you won't consider float number as a input independent parameter for your experimental result. Okay, but for the cases, okay, when this gravity force is important, you have to add this float number, as one of your independent parameters. Okay, so this is the three as I will say that most commonly seen dimensionless parameter you are going to see, okay, in the fluid mechanics, especially these two, okay, the Reynolds number and the Mach number. Reynolds number telling you that whether or not the flow will be laminar or turbulent, and the Mach number will telling you like whether flow is compressible or incompressible. Okay, this is the things. And there are definitely we have other kind of dimensionless parameters, but they are all for the individual kind of specific fields. Okay, you are going to see this Weber number, when you try to study the problem when the surface tension phenomena becomes significant. Okay, because that this web number is actually, if you see this rho v square L or sigma, this rho v square L or sigma, so actually this will be 1 for this web number, right? So this is the ratio between the initial over the surface tension. Initial over the surface tension force. Okay, you will have this web number consider. You need to add it for a problem. And similarly, okay, you can also define this the pressure force over the dynamic. So this is not the physical, so pressure force. Okay, so if the pressure force is important, you can define this Euler number here, because it's coming from this delta P over rho v squared, right? And similarly, okay, in the aerodynamics, so if for example for the flow over an air wing, important things like the drag force. This FD is drag force, and this FL is called the lift force, right? So you're using this drag force and lift force divided by the initial force. So you get those non-dimensional parameter called the drag coefficient and lift coefficient. And this CD and CL, so if you want to calculate the drag force, if you know the CD and CL, you just simply using this parameter to multiply this value. And this value is you already know. Okay. And this CD, CL, they are also dimensionless. You see these two in the aerodynamics a lot. Okay, they call the drag force and lift force, drag coefficient and lift coefficient. And if you have consider the two-phase problem, like if you have if you have the fluid, right? If you have the liquid, and you try to, if you try to, reduce the liquid's their pressure. Okay, if in some cases, if the pressure is reduced to not the liquid, okay, at the interface between liquid and outside, okay. So if you reduce the outside pressure, make it that pressure is even smaller than the vapor pressure of this liquid, the vaporization behavior will happen. So okay, so some liquid particle will just escape and to become the gas. And in that cases, you will form that small cavities, okay, because that gas inside the liquid will create small bubbles, right? And that small cavities for the gas. And in that cases, you can also define, this is cavitation number will become important. So this is the pressure is liquid pressure, this POV is the vapor pressure. And this pressure difference, again, okay, delta P here divided by this rho v square. So this cavitation number is important that if you have this cavitation phenomena due to this small phase changes, okay, between the liquid and gas, and so on. Okay, so so on this page is just the example to show you that additional dimension of this parameter you may meet in the future. Okay, but all this kind of this kind of dimensional parameter, we only use them for specific kind of fields. Okay, like this CDCL, we usually just use it for the aerodynamics and so on. Okay, so important things, this one, and this one. Okay, Reynolds number important to determine laminar or turbulent. Mach number important to determine whether flow is compressible, incompressible, flow is supersonic or subsonic. Flow number important when the gravity effect is important. Okay, so this three is required to remember. All right, and so let's talk the last topic of this chapter. Okay, so what we did so far? Yeah, here when we do the dimensional analysis. So when you do the dimensional analysis, right, it just give you that to telling you that okay, if you have a list of variables, okay, independent variables will affect your permanent data result. And after you do that dimensional analysis, after you do that Buckingham Pi theorem, actually you will reduce those parameters, right, into several dimensionless parameters, like the Reynolds number, Mach number, and so on. Okay, So it's showing you that your calculation definitely your the data you measure, right? That the dependent variable, like the example, like the drag force for the flow or sphere, the example I gave you in the last lecture. So that dependent variable, they will also be changed to a dimensionless parameter. Okay. So by doing this dimensional analysis, right, you see that okay, if we want to do experiments, we are going to see that okay, is this kind of dimensionless parameter is the things I'm going to to measure, to put, okay, to reduce, to put into my report. So because that it can greatly reduce, okay, the number of dependency, okay, because that we just need fewer dimensionless parameters rather than a lot of dimensional parameters. Okay, this is just one usage of it. And another thing from this dimensional analysis telling us is what? That is called so-called the similitude flow. What does it mean? That means that let's go back to using the example we use a lot in this chapter, that for that flow over over a sphere. Okay, so we're showing that at the end, right? At the end, right? We show that it will reduce to two parameters, right? So basically, this non-dimensionless drag, f over this rho v square divided by d square, d is the diameter, will be just a function of Reynolds number, right? So let me write it here. So we have this f over rho v square d square. It's just a function. It will be just a function of Reynolds number, right? Rho u d over mu. Okay. So what does this mean? This means is that because this is a dimensionless vector, this is dimensionless parameter, right? So which means that if we have two kind of problem, right? Two kind of problem. Both of the problem is the flow over sphere. Okay. But if the size of the sphere is not same, the diameter is not same, and also that the velocity field is not same. Okay. For these two problems, and but if the two problems, if they can reduce to the same dimensionless parameter Reynolds number, we because that we know that this non-dimensional drag force is only determined by the Reynolds number. So if for these two problems, if they can reduce to the same Reynolds number, we are going to know that these two problems will have the same non-dimensional or dimensionless drag force. And then so if I know the solution for this one, I just need to use calculate this non-dimensionless force from the data I measured here, and then just scale this one with this rho v square for this problem to get the force should be for this problem, the drag force for this problem. So this is called the similarity, so similitude flow. And this thing is very is especially useful for the experiments, because why? Because that in the experiments, okay, usually we will, when we try to do experiment measurements, right? For example, if we want to measure like the flow over this airplane in a wind tunnel, okay, and we know that the airplane is very big, right? So we cannot build a very large, wind tunnel can really hold an airplane with their actual size. We cannot do that because that it's very expensive to build a high-speed wind tunnel, and we just cannot build that size of wind tunnel with that large size. It's impossible. Okay, and even it is possible, but it will be just too expensive. So what we did, we just build a small wind tunnel, and then when we try to measure using this wind tunnel, okay, to do experimental study that to measure that the flow over this airplane, if we want to measure that what the drag force, what this lift force will be, okay, we usually just shrink this airplane to a small size, and we call this is the model size, okay, of this airplane, and put a very small model of this airplane into this wind tunnel. Okay, now the question coming to now the thing the question will coming out, right? So if we measure experimentally, okay, we in a wind tunnel we measure this small size, this modeled size the airplane. How we can make sure that the experimental data I measured in this case, okay, for this modeled size, can actually also valid for the actual, you know, um, actual those lift force, drag force for you know actual flight airplane fly with the actual flow conditions and the realistic. How we can guarantee that? And then now coming back to our dimensional analysis, right? So we just need to see that you know, if we can do this Buckingham pi theorem to study that what the function for this lift force or drag force for this airplane, so it will reduce to several dimensionless parameters, right? And if we can just make sure that all the dimensionless parameters to determine those non-dimensional drag force or lift force, okay, and this we have the same dimensional parameter in this wind tunnel condition as those dimensionless parameter in the realistic flight condition, like the Reynolds number if they are same. Okay, if the Reynolds number for this small model size here is same as the Reynolds number for realistic flight condition, and if the Mach number for this you know modeled condition, wind tunnel condition, and is same with the Mach number for realistic flight condition, and then we can see that okay, the lift force or drag force we measured, the non-dimensional, the dimensionless lift force drag force we measured here in this wind tunnel case will be the same dimensionless drag and lift force you know in the realistic flight condition. Okay, so this is something like you know we need to study more. Okay, and we call this kind of thing called the flow similarity and model studies, and we usually we will have a model which will be much smaller than a full scale prototype. Okay, and how we can guarantee that this two flow, this you know experimental condition, this model experimental condition, okay, is similar to your realistic flight condition. How we can guarantee that? Okay, so this is the criteria. The first thing you need to guarantee that you know geometric they are similar. What does it mean? This means that you know this model, okay, the airplane, this model airplane, you put it in this wind tunnel, it's just exactly it has the same geometry with your realistic airplane. You just shrink the whole airplane with the same scaling factor. Okay, so like if this is like a 1 to if this is 1 to 100 scaling, okay, everywhere should has the same scaling factor, so that if this geometry you just times that length, okay, by 100 times, it will just you know reproduce the realistic scale for the airplane. Okay, so this is the first thing we need to guarantee that you know for this solid item, their geometric they should for this flow problem, okay, their geometric should be similarity. Okay, this is for the airplane itself, and the second one, we also need to make sure that the flow condition is also similar. Okay, so what does the flow condition mean? The flow condition means that the velocity of the flow, the density of the flow, the viscosity of the flow, right? So we need to make sure that, you know, for example, okay, in the airplane, right? We know that in the realistic airplane, you know, maybe there is an attack angle between the airflow and the wings, right? So so when you do this wind tunnel problem, you also need to guarantee that you have the same attack angle of attack, okay? That you know, so that to represent the same problem, and all this kind of thing, so that in the end, okay, if you draw those streamline, you draw those path line for this flow for this to show the flow structure of this whole flow field, it will have the similar or even identical flow structure for the realistic case. Okay, so you need to make sure that for your flow condition, the flow condition after you need to, for this problem, they will generate the similar flow field, flow structure, okay, as a realistic problem. Okay, so this is called the kinematic similarity for the flow field. Okay, so this one is for this solid atom geometric similarity, and this one is for the flow field, fluid condition, and what's the interaction between these two is the force, right? Because we know that this flow after you hit this airplane, right, at the boundary between this flow and this airplane, you will create those drag and lift force. So the last thing you need to make sure that all the forces working on this model, okay, and those forces can also has a constant scaling factor, so that if you're scaling those force working on this model in this experimental condition with a constant factor, you can reproduce the actual force working on the realistic airplane. And this is called the dynamic similarity. The force will including all kind of the force, the gravity force, the the viscous lift force and drag force, and so on. Okay, determine all the force you need. And this is really the most difficult part to achieve. This dynamic similarity is very difficult part to achieve. And how we can achieve this is go back to this Buckingham-Pass theorem. You want to, from here to achieve this, you just need to guarantee that all these dimensionless parameters for the two problems, they are same. Okay, so to achieve the dynamic similarity, you just make sure that the Buckingham-Pass from the Buckingham theorem, all your dimensionless parameters, they are same. Same example for this drag on a sphere. Okay, you have this drag force equal to all these parameters, right? And after you do that dimensional analysis, you see that this dimensionless force is only a function of Reynolds number. Okay, so to ensure the dynamic similarity, you just need to make sure that in your model cases, your experimental cases, okay, your Reynolds number has the same number with the realistic problem, and we just denoting as the prototype cases. Okay, so if you can guarantee these two, and from this dimensional analysis, because we know that this dimensionless drag force is only a function of Reynolds number, then we can guarantee that the force, okay, the force, dimensionless force working on this model condition is same of the dimensionless force working on the prototype condition. Okay, so by this way we can guarantee that they are dynamically similar, because that the force, they are just varied to a same constant scaling factor. All right, and so this is the usage of this dimensionless parameter. Okay, by doing this Buckingham theorem, Pass theorem, and when you find this dimensionless parameter, you know that which one is important, which one is not important for your problem, then you can design your experimental study like actually you can design your experimental model so that that model can be not as big as the realistic one. You can just using this result you get here to scale your model, to scale your prototype to a model size, so that you can achieve the similar flows between your experimental measurement and the actual flow condition, actual flow problems. All right, so this is another usage for this Buckingham theorem, and this is called the flow similarity. Here we have an example to show you it. The problem is relatively simpler. Okay, it's the is like we just put again we put a sphere in a wind tunnel. Okay, and so that we want to achieve the similarity. The original problem, okay, the realistic problem is that we put this sphere actually into the water, into a seawater with this velocity 5 knots. Is nautical knots is the unit for the speed we're using the for the ship. Okay, so it's nautical miles per hour, and so originally it's for this sphere on the water, and now we move this we want to design a modeled sphere smaller than this one, but we put it into the wind tunnel. So we're using air to replace the water for the wind tunnel experiments. Okay, and so the problem is that so what's the velocity we should use in the wind tunnel for the air, so that we can achieve the similarity between these two. Okay, and if in the wind tunnel we measure the drag force is this one, and for the realistic problem for this sphere inside this sea water with this speed, so what the drag force will be. Okay, so the problem is pretty straightforward, because this is like the sphere and the drag on for the flow for sphere inside the flow, right? So we know that the only dimensionless parameter, independent dimension parameter, is the Reynolds number. So we just need to guarantee for the two cases, they just have the same Reynolds number. You have a Reynolds number model equal to Reynolds number of prototype. Okay, and so by this way, so first you do the first from the prototype problem, right? You know that for 5 knots, you just do the unit conversion to change their velocity to this feet per second, and then you calculate what the actual Reynolds number for this prototype problem. This is the Reynolds number, and then for this wind tunnel problem, for your model problem, you should achieve the same Reynolds number. Okay, so you also in the model number, you also should achieve this Reynolds number, and this is the model size, and this mu m has to use using the air, because now we replace the water to air. Okay, and then you can calculate that what's the to achieve this is the same Reynolds number, what's the velocity you need for the air for the inside the wind tunnel. You get it? Okay, and if in the model, okay, in the wind tunnel, you measure this drag force here. Okay, and then you want to calculate what the realistic drag force will be. You're just using this equivalence between this dimensionless drag force between the two cases. Okay, you substitute what you measured for the model, and then calculate this one, multiply by this value for the prototype problem. You calculate what the actual drag force you have, and you know in the end you find that the drag force for that sphere inside that seawater. So this will be the drag force will be. And remember that the one you measured for the one you measured in the wind tunnel is very much smaller, right? So this one, but the actual one after you scaling, this will be the one. Okay, so this is an example showing you that how to using this flow similarity. Okay, so to calculate the to convert to design, okay, of experimental condition, the model condition, so that they will have the flow similarity with the prototype condition. And then after that, if you measure some value in the modeled problems, you can scaling it back to get the corresponding prototype values. All right. And any questions so far? No question? Okay. And so so here in the textbook, actually they have some further discussion for this flow similarity. Okay. And by theory, okay, this flow similarity is very simple and is very powerful, right? You may feel like with this one I can just design any experimental setup so that I can scaling everything, okay, into a size that I can measure in the lab. I can scale all kind of flow condition into a flow condition which I can produce in the lab. Okay, you may think that, but in the realistic things is that for a lot of problems that is not possible. Okay, and one example I can give you here is this: if you have a ship, okay, and if you want to, if you have a ship, right, they are operating on the sea or on the river, whatever, okay, and if you want to measure their drag force, if you want to design a ship, right, so you want to in the design phase, you want to create a model of this small ship in your lab condition, and you want to see that can you create the same similarity flow condition, similarity flow in your lab in your lab. Okay, so let's take a look at this problem. Okay, and then I will showing you that why it's not possible. Okay, so if you want to study the drag force for this for a ship, right? Usually it will contain two kinds of the force, drag force. One kind of force is the same thing as before. Okay, it's a viscous force between the fluid and this ship. Okay, so we call it viscous force, and we know that this kind of thing is determined by the Reynolds number. Okay, and the second force is coming from the wave resistance, because that we know that the waves on the sea or on the river, right, they will create additional resistance force for your ship. And this wave resistance, okay, is usually coming from the gravity force. Okay, and so that the Froude number is important. Okay, so in another word, so if you want to achieve a similar flow in your lab, okay, you have to make sure that you have the same Reynolds number and Froude number. You create the same Reynolds number and Froude number as the realistic Reynolds number and Froude number for the realistic problems. Okay, and so let's starting from the Froude number. Okay, and so this is a Froude number for the model size. Okay, model is the one in your lab. Okay, and this is definition of Froude number. So you need to make sure this Froude number is equal to a prototype Froude number. Okay, so this one has to be equal to this one, and this will give you that. Okay, so if you want to achieve this one, okay, and usually, right, we will make our model size L. This L is the size, right? We usually want to shrink the ship, right, in our lab. So we make this model size of the L is much smaller than the prototype of the size, right? And if you want to achieve this Froude number of these two is same, you just need to adjust the velocity, right? Because g is constant, they cancel out. Okay, so you need to adjust the velocity with this relationship. Okay, for example, so if your model size is just 100 smaller, okay, 100 1%, okay, just 1%. If this Lm over this Lp is 1%, 0.01, then you just need to, in your experimental study, okay, for the flow, for the velocity of this ship, you just need to make sure that the model velocity should be just the 0.1 of your realistic ship velocity, so that you can guarantee that the Froude number is same. Okay, so this is what you can achieve from this Froude number equals same. Okay, and then let's take a look at the Reynolds number, because it's determined by these two number, right? So we want to achieve the flow similarity. We also need to make sure the Reynolds number for the model case and the prototype case is same. So this is definition of Reynolds number. This is definition of the Reynolds number. Okay, so make these two same. Okay, and again, you will see that the because that the velocity is already determined by from the Froude number, right? So you will see that, okay, so to achieve this one, so to achieve this one, the viscosity, okay, of the model case over the viscosity of the prototype case, okay, should be you has this correlationship. Okay, so you have to satisfy both these two conditions, because that this Rm over Lp is usually given, right? Because that we knowing that in our lab how smaller I want this ship will be. Okay, so if I have to achieve both these conditions, these two conditions, so that the flow have the similarity. All right, and so let's assume, okay, that I just want to shrink the ship by 100 to 1%. Okay, so what does this mean? That means that the velocity will be 0.1, velocity ratio will be 0.1, and the mu m or mu p, this one, based on these two value, it has to be 1 over 1,000. Okay, but the problem here is that in the experiment, right, in the realistic, we cannot find a fluid. There is no way we can find a fluid that their viscosity is only 1,000, 0.001 of the water. Okay, we cannot find a fluid for that. Okay, even the lightest fluid, even the most fluid with the smaller viscosity, example like the mercury the viscosity of the mercury may be smaller than water, but you cannot smaller to this range. That is not realistic. Okay, so yeah, in other words, we just cannot satisfy these two numbers at the same time. Okay, there is no way for us to satisfy in our lab condition to make sure that our both the Reynolds number and Froude number will be the same one with practical actual conditions. Okay, and so now we have the problem how we solve it. And so this kind of thing is called the incomplete similarity. So in this kind of situation, okay, instead we try to make sure that both the Froude number and Reynolds number is same. So maybe we can just neglect the Reynolds number, just make the Froude number is same to see that what we get. And then we can try to using some post processing. Okay, we make sure the Froude number is same. So we get some experimental data, and then we analyze the experimental data. We try to apply some fixes on the experiment data so that we can get the result will be close to the realistic solution results. How we do that? So this is something we can do here. Okay, so first thing, okay, we just make sure that the Froude number is same. We only match the Froude number. Okay, and then from our assume that in our experimental study, okay, to study this drag force, right? So you assume that this total resistance is what we measure. Okay, this is square here. This is measured. So this is but remember that this is from the experimental our lab condition, right? We measure this one. But remember this one, we get this one is we only match the Froude number. Okay. And remember what is the Froude number? Froude number giving us that what is the wave resistance, right? So yeah, in other words, right? If we can, we know that this total resistance will be the summation of both viscous resistance and the wave resistance, right? Oh no, and so if we can find these two curves, right? So we can knowing that the wave resistance will be actually the good value. But the viscous resistance actually is bad value because we didn't match Reynolds number. We only match Froude number. So this is the things that we can trust. And this one is something we cannot trust. Right? So what we can do? So we can just we need to apply some fixes, right? So that we can extract this we can extract this wave resistance from this total resistance we measure from experimental data. Because this is the things that really useful for us because we match the Froude number, right? So the things we can do is that we're using some analytical method, and for this shape over the for this viscous force for the shape, okay. Actually, we can instead using experiments, right? We can do some analytical study. Like we can using the things we will learn in the next chapter, okay. So things like so-called boundary layer theory, okay, for the flow over a flat plate, okay, using that boundary layer theory, because we know that later on we will know that this viscous force is only significant in a thin layer close to the wall, which is called the boundary layer. Okay, so for that boundary layer theory, okay, actually we have an analytical solution to estimate what this viscous force stress, what this viscous resistance will be. So we just apply that boundary layer theory, okay, with this experimental Reynolds number, because I remember that this Reynolds number, we have two Reynolds number now, right? One is Reynolds number is we use in the lab, and one is we write model, one Reynolds number used for the model, and one Reynolds number is used for the prototype. And remember that this in this case, these two is not same, okay? First, we're using this Reynolds number we use in this model. Okay, using this boundary layer theory, we can calculate it using some computer code, CFD, whatever. Okay, we can calculate what is the viscous resistance will be. So we can generate this curve. And then we're using our experimental, because remember this curve is measured from the experimental data, right? We're using this curve minus this curve. So we can get an estimated what the wave resistance we measured. So we get this curve here. Okay, and this wave resistance is a good value. Why? Because that we match the fraud number. Right, wave resistance is only determined by the fraud number. So this is a good value. And then we do the second fix. So this fraud number is good. And then we're using the same this boundary layer theory, but now we're using the realistic using the prototype Reynolds number to redo this boundary layer theory, so that we can regenerate the the curve with this viscous resistance from CFD or from other software or whatever. Okay. So, but remember, this one is generated using the correct Reynolds number. Okay, so you're seeing that, okay, this one, although maybe they are not 100% correct, but they should give you a good estimation. Now you have both these two curves, right? You add these two curves together, you will get your corrected, your fixed total resistance. So that you are seeing that, okay, for this curve now, because they're coming from the wave resistance with the measured wave resistance with the correct fraud number, and also coming from calculated viscous resistance from the correct Reynolds number. You add these two curves together, you get this fixed total resistance, and then you can think using this curve for your study. To you're thinking that this one can be working for the realistic problem, for the prototype problem. So this is what the thing can do. Okay. So in this example, so this is an example to showing you that how we do this incomplete modeling. Okay, incomplete modeling, which means that we only match one, or we cannot match all the dimensionless independent parameters. We can only match some of them, but it doesn't mean that we cannot get useful things. Okay, we still can get useful things from that. All right, and this incomplete modeling here in this example actually is overcome by using an analytical computation, that the boundary layer theory, to help us do that. Okay, and some other example including, so this is one example here, right, for this surface shape. Some other example is usually happens in the automobile industry, because that we know that we also put this automobile models into the wind tunnel to measure those drag force, aerodynamic drag force. Okay, and usually speaking, for the small size of a car in the industry, we usually shrink the size of the car, those sedan, like to the 3/8 this factor, so that it can fit for the wind tunnel. And if we match the Reynolds number, right? Because we are only consider the viscous drag, right? So if we match the Reynolds number, so the flow will be similar. Okay, so we can measure that from that wind tunnel to see that what the actual drag force will be. This is fine, but the problem is coming with the large size of the car. Okay, so if you have very large size of truck and bus, how you can shrink it and make it do a wind tunnel experimental measurement? So usually you have to shrink it more to fit the wind tunnel. So we shrink usually, okay, we have to shrink the truck and bus to actual size of 1/8 of the actual size. Okay, and now we want to fix the Reynolds number, Reynolds number M equal to Reynolds number of prototype. And so you have to using this because rho and mu is same, right? So you have to make sure that your U M of your L of M should be equal to your U of P of LP. Okay, because that's the viscosity and density is same for the air. Okay, so I just remove it. So what does it mean? That means that when you shrink this truck or bus smaller, make this smaller, and if you want to reach the same Reynolds number, you have to make your velocity larger in a wind tunnel, right? So smaller factor you use to shrink your truck, the larger the velocity you have to use. so that you can match the same Reynolds number in your wind tunnel and the realistic case. Okay, so but here is the problem. And when your truck is operated with a high speed like 100 miles per hour, okay, and after you shrink this truck to 1/8, and this UM you calculated, if this is 100 miles per hour, this UM you calculated will become very large. And when this UM become very large, and remember the Mach number, so you will make the local Mach number maybe larger than 0.3, so that the problem will become incompressible, from incompressible become compressible, so that you cannot achieve that flow similarity, that dynamic, what I say, you remember that we have the 3 similarity criteria we want to measure, right? So you may not, so that when the Mach number become very large, so this one you may not able to achieve it anymore, kinematic similarity, because that when the Mach number is large, you change the flow problem, you make the flow incompressible, from incompressible to compressible, and even some cases that if the Mach number is large enough, you may see those shockwave things. Okay, your flow structure is totally changed. So this is the issue when you measure that big bus. So in these cases, we still can try to match. Okay, let's assume we still match the Reynolds number. Okay, by neglecting this, maybe the flow will become compressible, incompressible. But you need to know that, okay, this is not a complete similarity. It's only incomplete, because that for this case is your flow problem, okay, will become incompressible, become compressible. So we have an example problem to show you that. So for this example problem, we shrink the bus from 1 to 16. Okay, 1 over 16, and by this cases, okay, so this is what you measure in the. So this is that drag coefficient, right? This non-dimensionless drag force with a function of the speed, okay? And so this is the result you measured in the experimental data, okay? And but the good thing for this problem, for this kind of problem in industry, is that what we find that if you plot if this drag force as a function with this air speed, okay, and if you plot that curve, Reynolds number as a function of this CD value, drag coefficient, you will see that this curve actually, when this Reynolds number become large, means that this air speed become large, right? In your experimental condition, you see that until after it reach to some value, right? This curve will become flat. So in other words, that means that after your velocity is large enough, okay, actually your drag force is not dependent on the velocity, not dependent on the Reynolds number. Okay, so what does it mean? That means is that remember that for these two cases, right? For these two cases, so maybe we can just assume that we reach to some condition, right? So for example, if this is the point, is that the one we measured in the model cases, and this point actually is the realistic Reynolds number P. Okay, but okay, this is the Reynolds number in the experimental problem. Okay, this is Reynolds number in the realistic case prototype. Although these two Reynolds number is not same, but because we know that the curve is flat, so that this should also give us the same result. So in these cases, okay, in our experimental data measurement, actually we can try to, reduce the problem, reduce Reynolds number problem, if we assume that is in this horizontal range, okay, so that we do not actually, we really do not need to, make sure that in our experimental measurement that this velocity had to be reached, had to become very large to match the same Reynolds number. No, we can using a relative smaller Reynolds number in our wind tunnel. Although the Reynolds number here and here will not be same, but because they are all on this same horizontal line, so they will give us the same result. Okay, so this is one example problem to show you that. Okay, and I won't go through the details of the example, and if you want to, you can try to read it yourself. All right. And the last thing, remember that there is also the cases, okay, where you want that the problem, okay, not only want to measure one parameter. Before we only want to measure that's the drag force, right? What is the cases that you have multiple dependent parameter? Okay, instead of the drag force, maybe I also want to measure the lift force, right? So that you know how I can guarantee that the drag force and the lift force I measured in that wind tunnel is the same one, drag force and lift force in the realistic prototype problem, right? So this is the cases that when you have the multiple dependent parameter, it's very straightforward. You just need to study each parameter, either the drag force or lift force. Just study each parameter and apply the Buckingham pi theorem on it, and find all these dimensionless independent parameters. Okay, maybe for the parameter 1 you want to measure, okay, phi 1 measure. After you do the Buckingham theorem, you know that it's a function of a Reynolds number only. And for the second parameter you want to measure, after you do the Buckingham, you see that it will function of a Reynolds number, Mach number, and you know, Floyd number, something. And then if you want to make sure that you know you have the similarity, you just need to make sure that you, after you do this one, you see that okay, your flow, if you want to make the total flow similar, you have to make sure this one, this one, this one. Okay, all these independent dimensional parameter you find, they have the same value. Then you can know that you know that both these two will be similar for the two cases. Okay, so it's pretty straightforward. And another example we can give here is this centrifugal pump. Okay, and when you have pump in industry, okay, there are two parameters we are more interested in, we're focusing on. One is the performance, because this pump usually to increase the pressure of the fluid, right? So this performance is usually calculated by the h, we call it the height. Okay, and this h actually is in the length of the in the unit of length. Why? Because that from that Bernoulli equation we have before, right? Remember that Bernoulli equation is p over rho plus v squared over 2 plus z equal to constant, right? So this is Bernoulli equation, right? So basically you will see that if the velocity is the same, and this p difference, pressure difference, right? P1 minus P2 actually can be characterized by the Z1 minus Z2. Okay, so actually we can using this length here to characterize the increase of the pressure. So this is what this height means. It is showing you that how much of the pressure is increased for the due to this pump for the fluid. Okay, and this is the performance parameter because when we're using the pump, right, we want to increase the fluid pressure. So this will be the performance parameter. The larger this value, the better we have, right? The better pump we have. And the second parameter we want to evaluate is so-called cost parameter. This is called power, because you need to provide power to that motor of the pump, right? So that if this value is large, which means that your cost is much larger than, is much larger for this pump. Okay, you study these two for some parameters. Okay, you do the Buckingham theorem. So for the first one, okay, you reduce them to them dimensionless. You see that this is called height coefficient, so non-dimensionalized for this h. And the second one is called the power coefficient, non-dimensionalized for the p. And the input dependent parameter, so this is called the flow coefficient. This q is the volume flow rate. This rho is density. This omega is angular velocity. This d is the diameter, and this mu is viscosity, right? And the second parameter is the Reynolds number. So after you do this study, although we have two dependent parameters, so if we want to achieve the similarity, we just need to make sure that both these two dimensionally independent dimensionless parameter, as long as they are same for the two cases, and then we will have the similarity. Okay, and so company similarity, after that we just need to make sure this is same and this is same. Okay, and so this one actually you can you can rewrite this one and to to get this one. Okay, it's the same thing. Okay, and for the pump, actually it's a complicated topic. I think it's a little bit about this course, the content of this course. Okay, so usually for the pump, okay, when you buy a pump, okay, usually in their manual they will give you this chart. So what this chart means, right? So the horizontal line is the volume flow rate, is Q, increase the volume flow rate, and the vertical line is three things. Okay, one is this power curve, right? This power curve is called what? It's called the system curve. So it's showing you that how this performance is changing with different volume flow rate of the fluid. And you also have this curve for the height curve. Height curve is this H curve. This we call it H height, right? So this is called the performance curve. So this is the performance curve. This is the system curve. System is the cost, right? So which basically the larger this one, the better, and the smaller this one, the better. Okay, so which means that if you apply this pump to a small mass flow rate, okay, it usually can very easily compress the pressure, make the pressure much higher, and with a relative low cost. So that's why is that you see the efficiency is really high. But until you increase the volume flow rate more, actually, the pressure you can increase for that pump will keep reducing, but and then the electricity bill you need actually will be also increasing. Okay, so this is something you want to read. Okay, and then if you draw the efficiency between these two, you will see that okay, this is the best operation point for your problem. So because this one give you the, relatively speaking, okay, it give you the better, the pressure increase with a lot of flow, and with a relative good, cost. Okay, so this is just some introduction, and also that sometimes they also introduce a new parameter. Okay, because this is a dimensionless parameter, this is dimension parameter. So if we're using this square root of this one divided by 3 or 4, this one, so you can define a new parameter, and this parameter is called the specific speed. Okay, so if you go to that pump manual, usually they will give you this specific speed as a parameter. Okay, to showing you that how well the performance will be, and not performance, efficiency will be. Okay. So this is just some introduction. Okay, you really do not need this. Okay, and we also have an example problem for this. So this is just some introduction. If you're interested, you just read it yourself. We do not need this for the exam and homework. Okay. All right. So here we finish this chapter here. Similarity, flow similarity, and we have 3 classes left after today's class, and that 3 classes we will focusing on the viscous flow. Okay, if there is a viscosity, how the flow will be. Okay, so that will be chapter 8 and chapter 9. But we will only introduce a part of the contents inside. Okay, we do not have time to introduce everything for the viscous flow. So we will just introduce the fundamental basics for the viscous flow. Okay, for the part of in the chapter 8, part of in the chapter 9 of the textbook. All right, and so we still have a little bit of time left. So let's quickly go through the the solutions for the midterm 2. All right, so let's stop right